Jai Hind everyone. So today we are going to discuss about the field effect transistor. So we have already talked about the transistor, bipolar junction transistor BJT, and today we are going to talk about the field effect transistor. So let us understand that what is the difference between the field effect transistor and BJT and what are the similarities. So in case of the BJT, we have studied common emitter, common base and common collector configuration, where common emitter and common base configurations, they are used for the voltage amplification, whereas common collector is having the voltage gain unity, so it cannot be used as a voltage amplifier, but instead of that it is used as a current amplifier. So it is used for current amplification factor. Also, in case of common collector, input impedance is very high and output impedance is very low. So that is the another reason that it is used for the multi-stage amplifiers, where the for the impedance matching device. So where it is used to match the high high output impedance of the first stage of the common emitter or common base amplifier with the high input impedance of the common collector. So this is how the impedance matching takes place, and it reduces the loading effect. Coming to the differences of the field effect transistor. So similarities are FET can be used as in case of the BJT, it can be used as an amplifier, as a switching device and impedance matching circuit. Coming to the differences, so field effect transistor and the major difference between the field effect transistor and BJT is that BJT is a bipolar device, whereas FET is a current control. FET is a unipolar device. What we understand by BJT, bipolar and the unipolar device, that bipolar means that current conduction in BJT takes place due to the two types of charge carrier, that is the majority charge carrier as well as minority charge carrier. Whereas in case of field effect transistor, current conduction takes place by single type of charge carrier, that is either electrons or holes. So if you are using N-channel field effect transistor, then majority carriers will be electrons, and if we use P-channel field effect transistor, then majority carriers will be holes. So the first difference is BJT is a bipolar device and FET is a unipolar. Second difference is BJT is a current control device and FET is a voltage control device. So what we mean by current control device and voltage control device? So in case of BJT, the output current of the bipolar junction transistor is controlled by input current. The output current does not depend upon it is independent of the output voltage. So it is that is the reason it is called as the current control device. Whereas field effect, in case of field effect transistor, the output current is controlled by input voltage. So it is a voltage control device because the output current is controlled by input voltage. So by varying the input voltage, we can control the output current in case of field effect transistor. Then field effect transistor has high input impedance because in field effect transistor, gate to source terminal is reverse bias. That is why it has very high input impedance, and that is the another reason that it has gate current almost equal to 0. Whereas BJT has emitter to base terminal forward bias and collector to base terminal reverse bias, and this is because of this reason input impedance of the BJT is less as compared to the input impedance of the field effect transistor. So FET has high input impedance, whereas BJT has low input impedance. Also, FET has is less temperature sensitive in comparison to the BJT. So because the BJT, in case of BJT, beta is temperature sensitive. So as temperature varies, beta changes, and if beta changes, then all the output currents gets changes. And because of this reason, also also the VBE of the BJT is temperature dependent, and also the leakage current of the BJT is also temperature dependent. So BJT is a temperature sensitive device, whereas field effect transistor is less sensitive to the temperature variation, and it is more easily integrated on the ICs. So these are the differences, that it is a BJT is a bipolar device, FET is a unipolar device, BJT is a current control device, FET is a voltage control device. The input circuit of the BJT is forward bias, so it has low input impedance as we discussed, and input circuit of the FET is reverse bias, therefore it has very high input impedance. Base current controls the output current, whereas in case of the FET, gate voltage, it is controlled the output current. So we can say that BJT is a current control device and FET is a voltage control device. BJT has more noisy and FET is less noisy. BJT size is in size BJT is larger as compared to the FET. So large number of field effect transistors can be manufactured on a same size of IC, and BJT are mostly preferred where the current is low, and in high current applications FETs are used. So coming to the field effect transistor, so there are we can classify the field effect transistor into the broadly into the two categories, that is junction field effect transistor and metal oxide field effect transistor. So again, junction field effect transistor can be divided into two categories, that is the N channel and P channel. And metal oxide semiconductor field effect transistor is divided into two categories, that is the N channel and P channel. And enhancement MOSFET again can be categorized into two categories, that is N channel and P channel. So we are starting with the junction field effect transistor. So what is junction field effect transistor? It is there could be the two types of JFET, N channel and P channel. So here we are discussing about the N channel junction field effect transistor. So this is the construction of N channel junction field effect transistor. Here we have a N type of substrate. Here we are having the N type of substrate, and in N type of substrate we take the for N channel junction field effect transistor. Coming to the construction part, so we take the N type of semiconductor material substrate and diffuses the two P type of semiconductor material. So because of the concentration gradient, depletion layer formation takes place. Depletion layer formation takes place. And here we have the two metal contacts with these two P type of materials, and which are internally connected. And this gives the gate terminal. And the top and bottom of the substrate is again connected to the semiconductor, to the metal contact, and one is the source terminal and another is the drain terminal. So these are the ohmic contacts, and this is the N channel. So because this is N channel junction field effect transistor, so the majority charge carrier, the current conduction will be takes place due to the majority charge carrier, that is electrons. So N channel, drain and source are connected to the N channel, and gate terminal is connected to the P type of the material. So we can understand the junction field effect transistor operations by a simple, there is an analogy between the tap water system and the junction field effect transistor. In tap water system, we have a water tank from where the water is coming. So source is the water tank, and there is a gate or the knob with the help of which we can control the flow of the water which is coming from the source or the or some water tank. And drain is the where we collect the water. So this is how we can and by controlling this gate terminal we can control the flow of the current. So similarly, in case of junction field effect transistor, with the help of this gate terminal, by varying this gate to source voltage, we can control the depletion width of the and by controlling this depletion width, we can control the flow of the current or flow of the charge carrier in the channel. So there is a strong analogy between the junction between the JFET and your tap water system. So source of the water pressure is the accumulation of electrons at the negative pole of the drain source voltage. The drain of the water is the electron deficiency of or holes deficiency at the positive pole of the applied voltage, and control of the flow of the water is the gate voltage that controls the width of the N channel by changing the depletion width, and the current will be or the charge carriers can be controlled through the channel. So there are the three basic operating conditions of the junction field effect transistor. One is the VGS is equal to 0 when we are not applying any voltage between gate to source terminal and increasing the VDS to some value. And second point is when VGS is less than 0 and VDS some positive value. And third is the how our junction field effect transistor work as a voltage controlled resistor VVR in the ohmic region. So that we are going to discuss. So initially, before starting the characteristic, let us understand that assuming that the substrate, the N type of substrate is uniform in nature, that means it has uniform resistance throughout the substrate. So this is your gate terminal and this is your source terminal, and gate to source terminal is reverse bias. So if it is reverse bias, that means this P should be connected to the negative potential and source terminal will be connected to the positive potential, and the voltage between these two will be VGS. And it is a negative voltage because negative terminal of the gate is connected to the negative terminal of the battery. And drain to source is also reverse bias, and drain is N type, so it will be connected to the positive potential of the battery, and source is connected with respect to source, and source is connected to the negative terminal, and this is plus and minus, so this will be at the ground potential or the zero potential, and the voltage between drain to source terminal is VDS. It is this voltage is VDS. So now, because we are assuming that the substrate is of the material is having the uniform resistance throughout the substrate. So when we apply at VGS is equal to 0, when we are applying no voltage at the gate to source terminal, and we are only applying the voltage between the drain to source, some positive voltage is applying. So as we are increasing this voltage, so this will attract the electrons towards the drain terminal. So as electrons are moving in this direction, that means the current of the drain current will be flowing inward, And if you measure the voltage, across the first resistance, it will be V is equal to IR. And if we measure the voltage between these two resistances, it will be twice of IR, because resistance will get added up. Across this, it will be 3R. Here to here, it will be 3R, and so on. So, it will be IRN. So, or NIR. So, here we can see that as we keep on moving through these resistances, and as we are going downward and downward, the net voltage drop across the resistance is also increasing, because the accumulation of the resistance values is taking place. And also we know that this voltage is a reverse voltage, because drain to source terminal is a reverse bias. So also we know that when we reverse bias a PN junction diode, it causes the depletion region, depletion width will start increasing. And if your depletion region starts increasing, that means, and because we know that the drop across the last resistance will be, it is more than the first resistance. So because of that, this depletion width thickness is also not uniform. It is minimum, and this thickness will be maximum as the voltage drop across the last resistance is maximum. So as we keep on increasing this voltage, the depletion region is also increasing, and it is not an uniform the depletion width does not increase uniformly. It is like an elephant-like ear structure, where the voltage, where the resistance is more, the drop will be more, and drop will be more. That means, and which is a reverse voltage. So that means the thickness of the depletion region will be more. So the depletion region will be touching each other at a faster rate as compared to the depletion region where the resistance value is less. So here we can see, as we increase this voltage as we increase this value VDS by increasing VDD, this channel width is keep on increasing. So here we can see that here we are having the voltage only 0.5 volt. Here we are having the 1 volt. Across this resistance alone we are having 0.5 volt. But at this point we are having the voltage 1 volt. Again here we are having the voltage 1.5 volt. So as we keep on increasing, moving in the channel, the voltage drop across the resistance is increasing, and this is a reverse voltage, and that is the reason here the depletion width is more as compared to the depletion width at the lower side. So as we keep on increasing this voltage, but VGS is equal to 0. So when we reach to the value when VDS is equal to VP, at that point both the voltages, both the depletion regions will touching each other, and when both the depletion region touching each other, that means there is a very less path is available, and through this smaller path all the charge carrier manage to pass, and so that the resistance will be very, very high. So let us understand this with the help of this characteristic curve. This is the case when we are keeping VGS is equal to 0. So when VGS is 0 and we are increasing the VDS, so charge carrier will, there are two things are happening. One is VGS is 0 and drain to source voltage we are increasing. So there are happening two things. One is that depletion region is increasing. Also the charge carrier in passing through the channel is also increasing. So if the charge carriers are increasing because of the positive potential of the battery, then the current is increasing. And if the current is increasing, so here we can see that when we are increasing the VDS, your current is also increasing. But as soon as this VDS is equal to VP, that is the pinch off voltage. What is pinch off voltage? It is the voltage when both the depletion regions will almost touching each other. That means there is a minimum gap left behind between the two depletion regions, and none of the then the maximum number of charge carrier would manage to pass through this small path. That means at that point of time your resistance is maximum, and after that your curve will almost get flat and the current gets constant, and this current is the maximum current which is flowing through the curve. And so this is the case when VGS is equal to 0 and VDS is equal to VP. At that point of time we get the maximum resistance through the channel and maximum current, and this current is called as saturated source to drain current. And if we increase the VDS beyond this VP, then no current is further increasing. Now next case is when we are increasing the VGS from the 0 volt to next higher voltage. That means because VGS is a negative voltage, reverse voltage, and gate is P type of channel, so definitely VGS will be a negative voltage. And if we increase, now initially we keep the VGS equal to 0, and at that point of time when VDS is equal to VP, we get the maximum current, that is saturated drain current, and drain to saturated source to drain current, and which is the maximum value. In the second case, we also increase the VGS from 0 value. So it is, let us keep it as -1 volt. So when you reverse bias gate to source voltage, and also we are reverse biasing the drain to source voltage. So the we are reverse biasing the input terminal, also we are reverse biasing the output terminal. So what will be the effect of the reverse biasing from two sides? Obviously both are the reverse voltages, so that the formation of the depletion layer or the depletion layer grows at a faster rate. And if the depletion region grows at a faster rate, what does it mean? It means that the number of charge carrier which manage to pass through that the path between the depletion region will be less, and if the charge carrier reduces, that means the current is reduces. If the current is reduces and path is getting narrower at a faster rate, that means the resistance is also changing. So this we can understand with the help of this characteristic curve. This is the drain characteristic curve. Why output characteristic is termed as the drain characteristic? Because drain terminal is the output terminal. So here we can see then when VGS was 0 and VDS is equal to VP, we get the maximum current, that is IDSS, and at that point of time we get the maximum resistance, the maximum current as well as the maximum resistance when VGS is equal to VP. Now when we apply now the voltage VGS is equal to -1 volt, then what happened at VGS is equal to -1 volt? Because the formation of the depletion region grows at a faster rate, that means the less number of charge carriers are flowing, so the current is reducing. If the current is reducing, then we can see that the resistance is at the lower value, the resistance is high. So resistance is also changing with the voltage. Then further we increase this VGS equal to -2 volts. Further, the number of charge carrier reduces and gets constant at a lower value. Again, this resistance is further changing. And as soon as we apply VGS is equal to VP, that is the pinch of voltage, then at that point of time, your current is reduces to 0. That means channel almost overlap each other. And if it is almost overlapping each other, means no charge carrier allowed to pass through the channel between two depletion regions. So current drops down to 0. So here it is interesting. If we join these locus of point, then we see that this region between 0 to pinch of voltage, this region is called as the ohmic region. Why we call it as ohmic region? Because in this region, your field effect transistor behaves as a variable voltage resistor. That means the resistance of that field effect transistor can be changed by changing the VGS. So it is the resistance of the field effect transistor can be controlled. Not only the current, but also the resistance of the field effect transistor can be controlled with the help of gate to source voltage. And that is the reason it is called as the variable voltage resistor. And it behaves as a variable voltage resistor when it is working in the saturation region. And it acts as an amplifier in the saturation region. So this is the region of operation where your device act as an amplifier or voltage amplifier and high current voltage amplifier, you can say. And in the ohmic region, it acts as a variable voltage resistor. So now the input characteristics of the field effect, this was the drain characteristic or the output characteristic. Now, how do we draw the input characteristic? Just we did in case of the field effect bipolar junction transistor. Here the drain input characteristics are also called as the transfer characteristic or transconductance characteristic, and the input characteristic can be calculated by using this equation. And that is the quadratic equation. ID is equal to IDSS 1 minus VGS over VP, where IDS and VP, IDSS is the saturated drain to source current and VP is the pinch of voltage. And by using these two voltage, these are the two specifications data which are giving in the specification sheet. These are known to you and these are the designed value given by manufacturer. So with the help of either we can draw the transfer characteristic with the help of this equation, or we can draw that transfer characteristic with the help of your drain characteristics. So here we can see that this equation is here, because we know that VGS is equal to, if we can keep the VGS is equal to 0 in this equation. If we keep VGS equal to 0 in this equation, then ID will be equal to IDSS. So we get this point. If we keep here in this equation VGS is equal to VP. So if we keep VGS is equal to VP in this equation, then ID equal to 0. Also, we can keep the VGS equal to VP by 2, VP by 4, VP by 8, and by using these values, by putting these values in this equation, we can get the subsequent points in between the 0 to VP voltage. So this is how we get this transfer curve. Also, this curve can be drawn with the help of this curve by just extending. Here you can see that because VGS is negative, so this is we are drawing it in the second quadrant, and this is your ID. So when VGS is equal to 0, this curve is we are having this point. When VGS is equal to VP, we are having this point. When VGS is equal to minus 2 volt, we will be having this point. Minus 1 volt, when it is minus 1 volt, we will be having this. When it is minus 2 volt, we are having this point, sorry, and -3, for -3 it will be this point, and VGS is equal to VP this point. So this is the curve. So either we can draw the curve with the help of your equation, quadratic equation, or we can draw this with the help of the drained curve itself. So this is how we can find the output characteristics and as well as the input characteristics of the field effect transistor, N-channel field effect transistor. Here mathematically it is shown here that if we use the quadratic equation of the current, drain current, then by putting these values we can calculate the various points of the transfer curve. So this similarly we can talk about the P channel. In case of P channel, we have P type of semiconductor material and two N type of pockets are diffused, and because of the concentration gradient, we have this depletion region formation. Again, drain to source terminal, reverse bias, gate to source terminal, reverse bias, and we can draw the input and the transfer drain characteristics and the transfer characteristics exactly in a similar manner. The only thing is, in the N channel, VGS was negative voltage, but in P channel, VGS would be the positive voltage. So this is all about the junction field effect transistor. Thank you.